So my name is S.V.N Vishwanathan. A lot of you know me as Vishy. And today what I'm going to talk about is joint work that I did with a bunch of people. Simon Günther is my postdoc, Alex Mola is my colleague, Nick Schrodov is my colleague, Chinhui Tiu and Jinyu are my Ph.D. students. And so let's get started. Typically what you want to do in machine learning is very simple things like, say for instance, you have these blue dots and these red dots and you want to find a classifier which can somehow classify these 2 points. Right? Or for instance, say you're given a bunch of digits and along with the labels and you want to figure out a classifier which can go and given some unknown digits can predict for you the labels on these digits. Simple tasks. So the core idea here is that in a machine learning context, your key, what you really want to do is to build a model which predicts well on data. So this is all that you care about. And the way you go and quantify how well or how badly a model performs on the data is by using a loss function. So think of a loss function as some kind of a sophisticated discrepancy score which tells you if you were supposed to predict this and you predicted something else, how much loss you incur or how much problems you incur because of them. So it's just a simple sophisticated discrepancy score. And depending on the problem domain you have, designing these discrepancy scores is a whole branch of research unto itself. The key challenge, the key difference between optimization per se and machine learning is the fact that you're not just interested in optimizing some kind of a function and getting to the minimum. Your challenge is that your model that you generate must generalize to unseen data. So this is the key challenge as compared to just optimization where everybody says, oh, I have an objective function and I just want to go to the minimum of the objective function. Right? So typically in a machine learning context, you'd find things where people say, I want to use a regularizer which is just some kind of penalty on my model. And again, designing regularizers is an active branch of research. People have their own favorite regularizers. I'll try not to get into that argument. But think of a regularizer as some kind of a penalty which says that these kind of models are more complex than the others. And so you want to choose from among your all possible models which could fit your data. You want to choose one which has low penalty, which is in some sense simple. Okay? You can put this whole thing what I gave you as an intuition in a more formal setup, which is the setup that we'll work with. So typically you assume that you're given some training data. So some instances, for instance, you might be given the digits and you're given some corresponding labels. So again, you might be given the labels on these digits. And the key goal that you have is that you need to find a model F. So in our case, the model F takes input data X and predicts a label Y. So that's what is the sole job of the model. And our goal is to learn a simple model. Right? So typically, you'd have this regularizer where omega of f could be any function which you think penalizes complicated models. And lambda is some kind of a trade-off parameter which tells you how much you want to minimize the loss on your data points versus how much do you believe in your regularizer. And your loss on your data points is simply the prediction of the model on xi and compared to the true label yi, and you just aggregate and average over all possible data points that you have seen. So this is a typical regularized risk minimization framework, and this is something that we'll work with for most part. Okay. Now you might ask, oh, what kind of loss functions can I use? A variety of loss functions that you could use, a variety of discrepancy scores that you could use. One possible discrepancy score that you might use and is quite popular in CRFs and such structured estimation problems is to find the maximizer of a log likelihood. So you assume that you're modeling a density in the exponential family and you just go ahead and you try to maximize the parameters of the model, you try to find the best model which maximizes your log likelihood. this is very popular and a lot of people do this. From an optimization viewpoint, this is again very interesting because this gives rise to reasonably smooth optimization problems, which in some sense are easier to handle. Another model which has become quite popular, especially again in the structured margin case, although I do refer to structured margin in this talk, I'm not going to talk about it further, I'm just using it as some kind of a motivating example. So here, the model under which the scenario is that you, at every point of time, you take the prediction of the model on all possible y primes. So you say, what is the score? So you think of now f as assigning some kind of a score to each one of the labels. So you take each one of the possible labels and you evaluate the score of f on that labels, and you predict with the label which gives you the maximum score. So you just have an argmax over the possible labels. And if you predicted y star and y was the true label that you wanted to predict with, then you incur a loss which is delta of y star. Again, there are very sophisticated ways in which you can design this delta function, this label loss, and again sophisticated ways in which you can come up with a model. Okay? The problem with working with this scenario is that it is non-convex. So it is non-convex in f, and if you want to estimate f, you run into all kinds of problems. We don't want to move too far away from convexity because things become ugly. So what you could do instead is that you could go ahead and try to upper bound this loss by some kind of a nice convex loss. So to see that this is an upper bound is very easy because you just take y, you substitute y star in here. So you get f of x y star minus f of x y, but this is always greater than or equal to 0 because by definition y star is the argmax, and then here you get a delta of y star. So you get delta of y star plus something which is non-negative, so therefore this is an upper bound. And this is convex, and it is nice to optimize. Okay. So let us see how this all works out in the case of binary classification, just a simple example. I generally tend to work well when there are some simple examples to see what's happening. So if you use this winner-take-all model for binary classification, then your labels, so you could encode the blue dots and the red dots as +1 and -1, so your labels are +1 and -1. And let's just assume that the model is y over 2 f of x. This is just, the y over 2 is nothing special, it just ensures that all the math works out nicely in the end. But you're just saying that f of xy is just the label times the prediction of the model on the data. Okay? And to output a label y star, you simply go and look at the argmax over your labels of y prime over 2 f of x, which is what we were doing before. But it's easy to see that this argmax is attained when you set y star to be the sign of f of x. So if you match the signs, then you're going to get the argmax. So this model is simply going to take your data, compute f of x, and predict with the sign of f of x. Simple model. The delta loss that you might desire to use in this case, there's nothing sacrosanct about this loss, but this is just one loss that you might want to design and use, and which seems quite reasonable to work with, is that if you get the label right, then you incur no loss. If you get the label wrong, then you incur unit loss. So what I'm plotting here is y times f of x, and if y times f of x is greater than 0, then I incur 0 loss because I got the label right. And if y times f of x is less than 0, then I incur unit loss. Clearly you can see that this loss is not convex. So what I can do is that I can upper bound this with a loss which looks like this. So the 0 term comes because when y equals y prime, then I incur 0 loss. When y is not equal to y prime, then I incur delta minus y over 2 f of x and minus y over 2 f of x. So these are, that's why the y over 2 was coming in. And you recover the well-known Hinge loss. Right? So you have a convex upper bound, and this loss is convex and nice. Okay. You can extend the same idea to multi-class Hinge losses, where suppose you assume that you have some k labels, and again the same kind of delta loss. So the delta loss is 0 if you got the label right and is 1 otherwise. Then if you write out the convex upper bound, again you get a max over y prime not equals to y, and then the plus just indicates it's a max over 0, so it's always lower bounded by 0. And then you get the delta f of x y prime and then f of x y. So this is the winner take all model. One thing that I did not talk about yet was how do you design the model. Again, there are many sophisticated ways that people come up with to design models, and this is one path that I will not go down on. For this talk, I'll just simply assume a very, very simple linear model. So I'll just assume that given data and label pairs x and y, there is some function phi. So this function phi you can think of as some kind of a feature extractor. So it extracts or asks questions about the xy pairs and gives you answers. Right? A simple, very, very simple way to think about it. And theta is a parameter. And what now you can see is that f of xy is completely specified by theta and phi. So what I need to optimize over is that I just need to get theta. There are two possible streams of thought here. People look at phi of xy as some kind of a infinite dimensional feature map in a reproducing kernel Hilbert space, and then you have to optimize theta, which is a function in an RKHS. But that's not the route we are going to go down. Again, we are going to keep it very, very simple and assume that this phi of x y is a finite dimensional vector, and so what we are optimizing for is a finite dimensional parameter vector. Okay. Now turning to the regularizer, so now you have to penalize models, right? So and we saw that our model is completely parameterized by theta. So in some sense, if you parameterize theta, if you regularize theta, it has the same effect as regularizing your model. And so one possible regularizer, which is very popular especially in the kernel community, is the square norm regularizer. So you say I want to get that theta which incurs the least loss on my examples, yet has the smallest length. Right? So this is just the notion of Euclidean length. If suppose you want sparsity in your solution, so in case you want to have sparse solutions, you want to have most of the components of theta to be 0, and this is something that you might care about, especially if you care about how fast prediction is, then you might want to do an L1 norm. If you're working with probability distributions, one possible and very popular regularizer is the entropic regularizer. Again, to keep things simple, for this talk, mostly I'll talk about square norm regularizers. Okay? A lot of what I'm talking is applicable to other regularizers as well, but just to keep things simple and nice. Now we turn to the question that we're interested in. So what's your optimization strategy for doing this whole thing? Right? To solve this regularized risk minimization problem, first of all the regularizers that I'm working with are convex. So they are convex in theta, and the losses, because of the way the winner take all model is a convex upper bound, so I have a convex loss. So overall what this gives me is a convex optimization problem which I need to solve. In the machine learning context, there are two different philosophies on how you can go around solving this convex optimization problem. The first one is to use an online algorithm. So in an online algorithm, you use small subsets of the data, and you assume that the data is streaming through, and every time you use a small subset of the data, compute gradients and the objective function value, and you take a step along the direction, and you just repeatedly cycle through your data. This is some area that I've done some work in, but again I won't talk about this today, and what I'm going to talk about today is batch optimization. So in batch optimization, you assume that you have the entire data set available to you, and you can compute the loss on the entire data set. So remember, in the regularized risk minimization framework, we had the summation over all possible losses, over all possible data points. And so I assume that all the data points are available at once, and I can compute the loss on all the data points at once. So this is what I'm going to talk about today. In batch optimization, again, you can do simple things like gradient descent, but they generally tend not to converge very fast, especially as you approach closer to the optimum. these methods don't work very well. So you want to do something smarter than just simple gradient descent. And so, but you still don't want to compute the Hessian, because theta in your case could be millions of parameters, and so you don't want to compute the Hessian, but you still want to do something smarter with the aggregation of your gradients. One possible approach to that problem is to use a bundle method. So bundle methods are something that Alex talked about, I guess, a few weeks ago. And the key idea here is that you use all the past gradients and you try to lower bound the function. And every time you get a new gradient, you improve your lower bound. And the key thing there is to figure out where to cut the next gradient. Where do you evaluate the next gradient so that your lower bound improves the most? Okay? This is the key challenge there. What I'm going to talk about today is another stream of work which is based on quasi-Newton methods. So what quasi-Newton methods do is, the idea here is that an Hessian might be very, very expensive to compute, but maybe I can approximate the Hessian. Maybe I can get a good idea of the Hessian by looking at the gradients. And if I have a good idea of the Hessian, then I can build a quadratic model of the function, and every time I can take a step on the quadratic model to reduce the objective value. So the key challenge here is that how do you use the gradients to update your quadratic model, and how do you take a step? So this is the key issue. These four gentlemen, Broyden, Fletcher, Goldfarb, and Shanno, in 1970 came up with the most popular quasi-Newton algorithm. So BFGS is basically by default a variant of BFGS is by default the optimizer that say MATLAB calls every time you call optimize. And I'm not saying that the MATLAB optimizer is good, but at least there's one that most of the people know about. And they independently of each other published essentially the same algorithm, and so it's named in their honor. BFGS is a default optimizer for basically not necessarily convex but smooth optimization problems. So this is where smoothness is very important for BFGS to work. So let's first understand what BFGS does, and then we'll see how we can apply it to some of the problems that we are interested in. So the way the BFGS algorithm works is that at every point of time it assumes that you can compute the gradient of the objective function, which is a reasonable assumption to make. So if suppose you are at iterate theta t, so you are at a current parameter theta t, and you can get the gradient of this objective function, and ht is an estimate of the Hessian. So this is the important thing, that it does not work with the true Hessian, it only has an estimate of the Hessian. Using the gradient and the Hessian, you can build a locally quadratic model. So it's just a second order Taylor expansion, so you have the value of the function, gradient, and the Hessian. But again, this is the estimate of the Hessian. To take a step to update your parameters, what you do is you find the next iterate as the minimizer of your quadratic objective function, of your quadratic approximation that you have of the objective function. Okay? It's not very difficult to see, just take the gradients and set it to 0, you can immediately see that this is how the updates look like. If you stare closely at the updates, you'll immediately see a couple of big problems. The first big problem is that you have to do the inverse of a matrix. If your parameters, if you have millions of parameters in your model, then you have a million by million matrix, and you're going to invert that matrix. This is of course very expensive. The second problem is that if ht is rank deficient, so if your function is not strictly convex but it's only convex, so there are flat regions in your function, then the ht inverse might not be well defined. So these are two problems that exist. Okay. And the third problem is that if you completely and totally believe this model, this approximation, this is only an approximation, this is not your true objective function. So this is not a true Newton step. So you don't want to take a full step. So first what people do is that they say, okay, instead of taking a full step, let me take only a step which I find by using a line search. So a line search is some kind of guard against saying, oh, I don't completely trust my model. I want to actually check that the direction that the model gives me is actually a good direction. And this direction, HT inverse of the gradient, is called a descent direction. A descent direction is one along which if you take a step, you will, there is an infinitesimally small step such that if you take that step, the objective value is guaranteed to decrease. This seems like a pretty trivial thing in hindsight, but in 1970 when Broyden, Fletcher, Goldfarb and Shanno actually discovered this, this was phenomenal. So they said that instead of maintaining HT, the actual Hessian, what if we maintain the inverse of the Hessian? So now you just maintain a vector BT, which is the inverse of the Hessian, which is an approximation to the inverse of the Hessian, and then now all of a sudden if you look at this update, instead of an order n cubed update which would have involved inverting a matrix, it's just order n square because there's a matrix vector product and an update. Okay. Then of course the question or the key thing in a BFGS algorithm is the B matrix update. So you update B by taking into account two conflicting requirements. One requirement is that you don't want to move too far away from your previous estimate of your Hessian, right? So you had some previous estimate and you got a new gradient, you only want to update it, you don't want to move too far away. How do you measure too far away? You measure it by a weighted Frobenius norm. W is the weights on the Frobenius norm. And this equation is called the secant equation. The secant equation comes about because what you desire is that the gradient of the model must equal the gradient of the objective function at the new iterate and at the previous iterate. So if you want to ensure this condition, it turns out the way to do that is to maintain the secant equation. So the secant equation is in some sense a relation between movement in the gradient space. So this is how much you move in the gradient space, and this is how much you displace in the parameter space. So this is some kind of equation which relates these two. The W is basically where the black magic in BFGS is, and what is amazing to me still is that all four of them came up with the same weighted matrix. But if you use the right weighting matrix, it turns out that the update for B is just a rank 2 update. So you do a projection into a so you deflate into one smaller dimensional space and you have a rank 1 update. And the limited memory variant of BFGS is one which just uses a low rank approximation. This is what is called by MATLAB by default. So you just keep a few columns and you approximate B by a low rank matrix. Okay? And of course, to satisfy the line search, to do a line search, typically people use what is called a Wolf condition. More than the equations, a picture gives you a much better idea. So what it says is that you look at the one-dimensional convex function. So you're given a direction. Remember that that direction is a descent direction. So if you take a step along that direction, your objective function will decrease. Look at that one-dimensional convex function, which is along the direction of descent. Here is the gradient of that function, this first order Taylor approximation. You push it up a little bit. And now your step size should not exceed this. Why does this make sense? This just ensures that you don't take too large a step size and actually end up increasing your objective function more. The second condition simply says that this condition does not prevent you from taking too small steps. So the second condition simply says you have to take the gradient and slightly increase it, and your step size should not be smaller than this. So the first condition ensures that you don't take too large a step. The second condition ensures that you don't take too small a step. So you want some reasonable step size. Okay. Now when we want to apply BFGS to machine learning problems, you have trouble. The main problem is that BFGS has this assumption of smoothness. But if you look at some of our losses, they're clearly not smooth. Right? At these locations, these losses are not smooth, and so, well, we have a problem. How do you solve this problem? To solve this problem, you have to understand a little bit more about gradients and the generalization, which is called subgradients, and you have to go back to high school, at least to get the intuition. So The intuition, so remember that in high school you were taught that given a one-dimensional convex function, I'm just plotting everything in 1D just to give you an idea, but of course things are more complicated in higher dimensions. But to get the gradient of a one-dimensional convex function at a given location, you just drew a tangent line, and then that tangent was your gradient. The other key property of a convex function is that this gradient line, this first order Taylor approximation, is always a lower bound to the function. So you can draw this gradient line and you'll always see that the function lies above it. Now let's try to apply the same intuition to our favorite Hinge laws. Can you produce for me a line which is tangential to this Hinge laws at this location and lower bounds this Hinge laws? Well, here is one line. It is tangential to the Hinge laws and is lower bounding it at every location. The problem is, here is yet another line, and here is a third line. So what happens is that at this location for the Hinge laws, there's not one gradient, but there are many gradients. You can actually, it turns out, formalize this notion, and this yields the notion of what is called a subgradient. So mu is called a subgradient at a given location if the first order Taylor approximation that you make with mu is always lower than the actual value of the function at any location. Okay? And if you collect this set of subgradients, then you might get a set, and this set is called a subdifferential. In fact, the subdifferential is a strict generalization of the notion of gradients, because when the function is differentiable, this set contains a singleton, and that singleton is exactly the gradient of the function. And the even more amazing thing about convex functions, especially, is that they are subdifferentiable everywhere. So in the relative interior of the domain. So there are some small technical conditions, but in all the places where you would care, a convex function is strictly subdifferentiable. So a subdifferential exists. I call this subdifferential set has these three properties which I call the good, bad, and the ugly parts of the subdifferential set. So the good part is that the subdifferential is always convex. At any location, if you look at the set, the subdifferential set, it's a convex set. The bad news is that every subgradient is not a descent direction. So key property of a gradient is that if you take a step, an infinitesimally small step in the negative gradient direction, it's a descent direction, which means that you can strictly decrease your objective function. To see that this is not the case for subgradients, just think of a V channel, right? So you have a V function. At this location, take any subgradient and take a step. Even an infinitesimally small step is going to take you out of this point, which means it's not a descent direction. This is the key, this is the major problem when working with subgradients. In fact, the ugly part is that there is only an implicit way, or there's this one condition that you need to check always to ensure that some direction that you produce is a descent direction. So D is a descent direction only if you take the dot product with D with all the elements of your subdifferential set, then it is less than 0. In other words, it makes an obtuse angle with every element in your subdifferential set. And this is the ugly part of working with subdifferentials. When you work with subgradients, three things in BFGS break down. The first thing is that your locally quadratic approximation is not well defined. Okay? The second part is that the descent direction is no longer well defined because there's no gradient, there's no single element here, so what is a descent direction? And the third problem is that the line search, the Wolf conditions for the line search are no longer valid. So you have to modify all three. So I'll show you how to systematically modify all three. To see why the locally quadratic approximation is no longer valid, let us look at quadratic approximations with three different subgradients. So I just plug in three different subgradients, and you can see there are three different quadratic functions which fit at that location. This is terrible, and I don't want to work with this. So what I might try to do, and this is what I'm going to do, is say, let me take the envelope of these quadratic approximations. So I take the sup over all possible subgradients of this quadratic approximation. So each one of these subgradients is giving me a quadratic ball, and I'm going to take this sup ball. This is very nice except for one problem. The problem is, if you look at this approximation, this is no longer quadratic. It is piecewise quadratic, but it is not quadratic. And so I just call it a local pseudo-quadratic approximation. Okay? Now to take a descent direction, to find a descent direction, you have to actually go and find a descent direction using this locally pseudo-quadratic approximation. So what you might do is that, okay, so you have to do an argmin over theta of this, because this is your model now of how the function locally looks like, and you have to find the next iterate. One standard trick that you can do in optimization is you can take this linear part, add a slack variable, and add it into the constraints. So this is a standard trick that you can do. Take a part of your objective function and shift it into the constraints. This is significant because now I am changing the problem of finding the next iterate or the next direction, the next parameter into a constrained optimization problem. And even more, this could be a very large set of constraints because you have to enforce this for all possible subgradients. I could be lazy and say, instead of doing it for all possible subgradients, what if I just enforce it with respect to a few subgradients? And the key trick is that I have to be able to produce these mu i's, this sequence of subgradients, in such a way that the optimization problem that I solve, this finite dimensional optimization problem that I solve, actually becomes closer and closer to the actual optimization problem that I'm interested in, the direction finding that I'm interested in. So I'll show you in a minute how to generate this sequence of mu i's. Okay? And so my plan, or what we do, is that we take this pk of d is an lower bound to the direction finding problem at step k, and every time I make this lower bound better and better by producing these sequence of mu i's. How do I do that? This is an algorithm which I call descent direction finding by column generation. So what you do is you start off with an arbitrary direction as your proposed direction of descent. You assume that there is some kind of an oracle. So especially for hinge losses and generalizations in machine learning context, it's always easy to produce such an oracle. So what the oracle does is that given this direction, it in some sense gives you the most violating subgradient. Why is this? Why do I call this the most violating subgradient? Because if you look at this constraint, this is a constant, and so the violation happens only because of here. So I'm trying to get the most violating subgradient at every point. I ask the oracle for that most violating subgradient. If mu k times dk is less than 0 for the most violating subgradient, then I'm done because I've found a descent direction. You remember the condition for the descent direction was dk times mu k must be less than 0 for every mu k. So if I check this, and if it is less than 0, I have a descent direction, I go off. On the other hand, if that is not true, then I find my next direction by solving this pk, this approximation, this kth approximation. And I keep repeating until I find a descent direction. This kind of looks weird because to find a descent direction, you're solving a very hard optimization problem. It's a quadratic program. And every time to find a descent direction, if you solve a QP, this kind of doesn't feel right. Turns out that you can replace the QP by just doing a one-dimensional optimization problem in alpha. So this is some kind of a line search between your current iterate and your next iterate, and then you just do a line search and you take a step along that. The good news is that we can actually show that this algorithm converges very fast. So it converges very fast and you can find a descent direction very fast. So all that is good, and the last thing that I need to fix is the Wolf conditions. So I call this the sub-Wolf conditions because I call my algorithm subBFGS for subgradient enhanced BFGS. Again, the picture tells you more. The idea is that at this location, if your function is non-differentiable, then you have many first order approximations. You choose the tightest one, and then you lift it up. So that's what the first line says. You choose the tightest approximation, and then you lift it up, and you take a step which is no bigger than that. And again, for finding the smaller step, you take the tightest approximation, and then you lift it up, and then find the point. And so your step is no smaller than this. Okay? In fact, if you go back to the Hinge laws, things are even nicer. If you look at any direction and you plot this objective function, so you take any direction and you move along this direction, this is nice and quadratic. But actually the problem is when you zoom in, you see that the ugly parts of the function show up. So you see these kinks in the function. So this is just a zoomed in version of the objective function. But because it is piecewise quadratic, it's very easy, in fact, to characterize and actually compute these kinks. I won't bore you with the details. If you want, please talk to me. But the basic idea is that you can compute all the kinks along any direction. And since you can compute all the kinks, you can do an exact line search given any direction. So this is a key property of the Hinge laws, which we can exploit to do an exact line search. And the exact line search, of course, satisfies the subwolf conditions. Here is a very simple problem to illustrate how subBFGS works on a problem. So it's a particularly evil problem for BFGS. So what you do is you have a channel which looks like this. Along one direction, there is 100 times more curvature than along the other one. So it's very steep along one direction and very shallow. It has some gradient, but it's very shallow along the other direction. So it's got 100 times more curvature information along one dimension than along the other. If you run BFGS on it, so what I'm plotting here is how does the iterates go. So I'm looking at it from the top, and I'm looking at how the iterates go. So I start from here, from some one corner, and I get a gradient direction. So I swing to the other place. I get another gradient direction. I swing to here. But since along this one direction, I'm getting 100 times more gradient information than the other, what happens is that I swing wildly along that direction, but I make very little progress along the other one where I have very little gradient information. And so after a while, you see if you run, it stagnates, and it never gets to the solution. So this is particularly evil for BFGS. You can try, one possible quick fix might be to say, oh, what if I modify my wolf conditions, or I modify my line search to ensure that if I end up close to the hinge, to these channels, to these valleys, I don't actually, I push my parameter away from that. So I still try to satisfy my wolf conditions, but I push my parameter away from these hinges. If I try to do that, it turns out that BFGS does converge, but very slowly. On the other hand, if you run our sub-BFGS, sorry.
When you say BF in your last slide, is that loss itself is non-smooth right now? It is smooth.
No.
I mean, it's not smooth, right?
Yeah, it's not smooth.
So how are you using the BFGS?
So you can still use BFGS as long as you never end up at one of the hinge points. Because
so basically just to use BFGS out of the box.
Yeah, just BFGS out of the box. So the first one is BFGS out of the box. That one is BFGS out of the box. This one is where we modified the line search. So we modified the line search in BFGS to say that consciously we will try to keep away from the hinges. So when you're
the optimal point actually on the hinges somewhere.
Yeah, the optimal point is on the hinge.
And you try to stay away from that.
Yeah. So the problem happens because you want to along one direction you're getting too much gradient information, and so if you get to the hinge along that direction, then you'll no longer make any progress. So only along that direction we are trying to keep it away from the hinges. This is just a line search which says that if I have a point which can keep me away from the hinges, then I will preferably go to that point. That's all. So it's just a simple line search with one modification, with one extra condition.
I still don't understand why, eventually, you hope that the curvature information will be propagated so that it knows do like the other direction as well. Why that is not the case in the example? Why?
So it eventually goes to the solution, but it takes a long time. So it just keeps on doing. So if you look at it, it just goes like that, and slowly the oscillations die out and it goes to the hinge. That's what is happening. So it's doing this. So it starts from here like that. Okay. We can take this offline. Yeah. And if you use subBFGS or algorithm, so at the first step you start from here, you get a gradient direction, you do a line search. The line search lands you on the hinge, right at the first iteration. At the hinge, our direction finding kicks in, and it kills all components of the descent direction along any perpendicular direction and points you straight towards here. And again, our second time, our line search kicks in, and the second time it goes straight to the optimum. So in 2 iterations it's converged. So it's a contrived example, but shows where the problems in BFGS are and how we can try and fix them. On some real data, on some quote unquote real data, how this performs. So this is again only with the binary hinge loss, and so we compare against BMRM. BMRM is our bundle method solver. This is the solver that Alex talked about a few weeks back. OCUS is a version of BMRM with a line search. So it's basically a bundle method enhanced with a line search, and it's currently reported to be the best optimizer for these kind of problems. And subBFGS is our algorithm. And you can see that OCUS, for instance, has a bug in its line search. So there's a problem with its line search. So I'm talking to Soren to fix that. But they have a bug which basically makes the objective function oscillate and go all over the place. BMRM starts off reasonably well. In the middle game, it's not very good. But towards the end, it kind of catches up. So you can see this is the zoomed in plot. If you look at, this is, by the way, I must mention that all the values of the regularization parameter that I report are just from Soren's paper. So these are not something that we dreamt up. He just did some cross-validation experiments and came up with these best values, and we just used them. Okay, here is another example where we ran this on Reuters, and you can see one thing that happens in most of the experiments we see is that subBFGS actually in the initial phases converges very, very fast. So it decreases the objective function very, very fast. Towards the end, as you come closer and closer to the optimum, it plateaus out. It tends to plateau out a bit more. On the other hand, if you look at BMRM, it takes a long time to start making any progress or start reducing the objective function in any reasonable way. But towards the end, in the end game, BMRM is pretty good. So what we are plotting here is what happens in the end game. This is some behavior that we observe across a lot of data sets. This is on astrophysics, similar kind of stuff. And similar things on cover type. So to finish, the quasi-Newton philosophy is to use the gradients to build a quadratic approximation and then take a step on the quadratic approximation. Initially, this is a very good fit. This is a very good thing to do right at the beginning, because at a coarse level, even though you have hinges and you have non-smooth points in your function, a quadratic approximation, a smooth approximation is not a bad approximation to work with. But as you come closer and closer to the optimum, somehow the hinges matter. So it seems that BFGS, the sub-BFGS that we have, is not able to handle or is not able to work very, very well. I mean, it still in asymptotic performance is similar to BMRM, but it's not much more superior than as it happens in the beginning. And we conjecture that the reason is that near the optimum, the hinges actually matter. So your progress slows down. If you're working with a quadratic model, but your actual underlying function is not smooth and has hinges, then you have trouble. the other thing that is very important in subBFGS is that it requires a line search which needs to fulfill the Wolf conditions. BMRM, for instance, does not need any of these line searches. And for a binary hinge loss, if you want to do an exact line search, then it's very cheap. You can just, because of the observation that it's a piecewise quadratic function, you can get all the hinge points, you can do it very fast. In fact, you can do it for any loss with a finite number of classes. So, I mean, for all the multi-class, multi-label kind of losses, it's easy. I mean, this is work in progress. We have very preliminary results, but we can manage it. The big open question that I have, and I'd really like to talk to somebody if they have answers, is if you have a structured loss. So even in a simple chain, just take a simple chain graphical model, and you want to do a line search. So I give you a direction, and I tell you that you have a parameter and you have a direction, and if I ask you to do a line search, it seems rather difficult because the aggregation happens over many parts of the chain. So if you have some ideas, please talk to me. Finally, to conclude, there are two fundamental ways to use the gradient. There are the quasi-Newton methods or the bundle methods. I've done work in both. Today I talked to you about quasi-Newton methods. And we systematically modify them so that we can work with non-smooth problems that arise in machine learning. And in general, our solvers are more generic and faster than hand-tuned variants. So we want to build more black box solvers rather than solvers which are very, very tuned to the problem. And even then, of course, just building a black box one is not important, is not useful. You have to make it fast. And it can be used in a wide variety of machine learning applications. I must say that there is still, I mean, this is very recent work. It's just submitted to ICML. So this is still a lot of work needs to be done. Thank you very much for your time and attention. Yep.
I was thinking as I was listening to your talk about that question, the generic versus hand-tuned variant. And for the particular setting you described, with hinge loss plus L2, I was realizing that it seems to be actually there's a lot of geometry there that the generic method cannot exploit well. Particularly when you're thinking about this, essentially you have a polytope and then you have some kind of quadratic contours on each face. Can't you do a lot better and with even the most carefully tuned generic method?
So to answer your question, what we are doing here, for instance, is some kind of interpolation between the two, right? It's not a completely generic black box solver where you just plug in and things come out. For instance, the line search knows exactly what the objective function is and how the objective function along a particular direction behaves. So we use that, but we are not completely tuning it only for that particular application. You're right that if you actually had a completely tuned solver for that, I don't know what you would use as your base algorithm. You would have to start from some base algorithm. So what we are trying to do is somewhere in the middle, saying, okay, we know something about the objective function, but it's not completely black box, but we don't want to be completely for that problem. So that's the idea we have.
In the sort of experiment, so you basically list with hinge loss plus L2. I'm wondering what if you do other like smooth functions like log linear models with L2. Does this particular method, how does this method compare with just a naive, plain vanilla BFGS?
It just reduces to plain vanilla BFGS. If your function is smooth, it's identical. If your function is a smooth function, so you have some log linear model plus some quadratic regularizer, identical to BFGS.
So you're saying that do you have to manually switch that the direction search?
No. In that case, there's just one element in your subdifferential set. Your oracle just returns that, and you're fine. So you don't have to do anything. You don't have to know that your function is smooth beforehand, but it will just reduce to BFGS. Oh, Corina has going. Yeah.
Yes,
Sorry, you should look that way.
So there are clearly 1,000 other ways that people over the years have dealt with non-smoothness and quasi-Newton methods. Can you comment
Yes.
on why yours is better or where it's better?
So there is an active line of research, especially in optimization, to use quasi-Newton methods for non-smooth optimization. Typically what they tend to do is that they of course change the model in the same way that we do, but one key thing that they miss, or one key thing which is important or good for which is which we exploit a lot, is this line, that you can get, given a direction, right, you can find a subgradient which is the most violating subgradient given that direction. This is something that we exploit a lot. What other methods typically tend to do, so another way to think about it is that we sit on the point of non-differentiability and we repeatedly sample the subgradients at that same location. Most of what other people do with quasi-Newton methods for non-smooth optimization is that they make small steps outside and they sample the gradients outside. So you're sitting at a point of non-differentiability, but you sort of step out a little bit and you try to build your model based on the gradients that you sample close to where you are. But this in machine learning, for instance, tends to be very expensive because every time you have to evaluate the gradient at a new location, and that is very expensive. Here, you're just sampling the subgradients at the same point. So you're never moving your parameter out. You're staying at the point of the hinge and sampling the subgradients. Does that answer your question?
Yeah, I just wonder why in your experiments you're not comparing to any of those methods at least.
Oh, it's just we intend to do it. It's just this is really preliminary work. I mean, I've just, as I said, we just submitted a paper to ICML. We are still understanding a lot more things about the method. We do talk about some of this in our paper about what the philosophies are, but we haven't done any experiments yet.
Thank you.
Thanks. Yep. Yeah. Sure.
So how does this thing work? Like Hinge plus L1 type of regularization? Does it introduce any?
No, it can work with L1 plus Hinge.
And last year there's this paper all using this.
The online Orth and Weiss LBHS.
Yeah.
So actually it turns out that we can use a direction finding algorithm as a plug-in component into Orth and Weiss LBFGS, and it actually improves the algorithm. So they have this, well, I won't call it ad hoc, but they have one way of doing a direction finding, but this loop that we have, actually if you plug this into Orth and Weiss LBFGS, it improves the convergence of the algorithm. So you spend a little bit of time to find a better direction, descent direction. They have one way, they have a deterministic way, so they always choose one direction and just step along that. But if you spend a little bit time, it turns out that you do much better. So we have some experiments where if you just run this direction finding loop, Orth and Weiss LBFGS improves. Yep.
Do you have some kind of fuzziness in your numerics in case your line search doesn't exactly hit the kink?
Yeah, you know when you're actually implementing a solver, you have to be careful about all these things. I mean, underflows, overflows, everything happens. So in real life.
So my other question is, did you somehow evaluate this in case you don't exactly have a kink, but you just have something that's very sharp, but not excellently non-differentiable? Because you can imagine having a function that if you think something expansion, you can approach the kink from a smooth function, and at some point you would think that your method would be off even if your function is strictly speaking differentiable.
Yeah, I mean you're right. I haven't come across a machine learning problem where I I would have this kind of a scenario. But you're right that if your function is in the limit approaching a hinge, but it's always, you just take a smooth function which in the limit approaches, say, a V function, then sure, BFGS would still have problems and you would have to modify it. So, but I haven't come across a problem. Sorry. You had a question, Fernando?
No, it's kind of too long. We'll talk
Ah,
about it
okay,
later.
yeah.
Okay, let's thank the speakers again.